Hello, my name is Caitlin Rodriguez Rivera, and this is my Physics 2211 video lab report for Lab 3, Black Hole. Here is a table of contents providing an overview of the topics that will be covered in this report. First, I would like to briefly touch upon the purpose of this experiment, which was to find the mass of a black hole through a simulated gravitational interaction between a star whose mass was known and the black hole, and taking these findings and calculating an initial velocity the ship would need when leaving the planet to not crash with the planet or the black hole when flying back around. Below on the slide were my findings with the mass of the black hole being 1.51972 times 10 to the 34th kilogram and my spaceship's initial velocity being negative 4.3 times 10 to the 7th power in the x direction and 2 times 10 to the 6th in the y direction. The fundamental physics principles of Newton's second law relates the net interaction between system and surroundings to the change in momentum that it undergoes, also known as acceleration over a change in time. Some formulas of importance within this experiment include the position update formula and the velocity update formula, which can be formed by Newton's second law, that work in concurrence with the initial information gathered from the first computational model to make the second move. Parallel and perpendicular components are a key concept that come into play when the system is not in equilibrium, which in this case is due to a constant change of direction, revolving around the black hole. The parallel component is referred to as p hat and points in the direction of motion, representing changes in the magnitude of the momentum, speeding up or slowing down. The perpendicular component is referred to as n hat and is positive towards where the object's trajectory is turning, representing changes in the direction of momentum, turning. At the bottom of the slide, we can see that these two components go into calculating the net force of the system. Another concept of importance to this experiment is the universal law of gravitation, formulated by Isaac Newton, that describes the gravitational attraction between two objects with mass, in which they exert gravitational forces on each other that are equal in magnitude but opposite in direction. It involves a gravitational force formula that takes the gravitational constant, the masses of both objects involved, and the distance between the two centers of the masses. The gravitational constant is a fundamental physics constant that denotes the strength of the gravitational force between two masses. Here are some introductory aspects to my computational code for part 1, such as the initial conditions, including the gravitational constant, mass of the star, and the time interval between data points, along with some equations that were coded in. The first was the parallel component of our net force. The second was the mass of the black hole, which we found by rearranging the gravitational force equation. Here is the computational code for part 1 in its entirety, with the system being the star and the surroundings being the black hole and space. In order to find the mass of the black hole, we needed to find our net force that we found after calculating the change in the star's momentum, before calculating our parallel component and subtracting it from our net force to find our perpendicular component. We were able to find the mass of the black hole using the gravitational force equation rearranged. Here is a result of my computational code for part 1 and some associated values. Some possible sources of error for these values would have been the rounded values that were taken at each step, and possibly increasing the amount of runtime for the program to have garnered some more values to obtain a more accurate average mass. Here are some introductory aspects to my computational code for part 2, such as the initial conditions with the mass of the black hole found in part 1 now coded in, and the initial velocity of the spaceship found through a trial and error method, along with some initial equations coded in, the first being the net force on the planet, and the second being the net force on the ship. Here is the computational code for part 2 in its entirety, with there being two systems, the star and the planet, and the surroundings being the black hole and space. Within our calculation loop, we coded for the net force on the planet and on the ship, along with applying Newton's second law and the position and velocity update formulas to make the planet and the ship move, though the initial velocity, as previously mentioned, is found through trial and error. Here is a result of my computational code for part 2 and some associated values. As we can see, the ship is shot out of the orbit of the black hole since the speed of our ship was greater than what was needed to escape. Some possible sources of error are again the rounded values that we have been using in the trial and error method that we used to get our initial velocity. Now to address some additional questions. While net force and rate of change in its components are similar, net force also considers the mass of the objects, which we do not possess as initially for the black hole, and which makes it easier to find the rate of change over time with what we already possess. The initial velocity my spaceship would need to enter into some kind of orbit around the black hole would have to be lesser in magnitude in the x direction, and greater in the y direction in order to fall in more vertically, and after some trial and error I was able to produce an initial velocity of -2 times 10 to the 6, 10.7 times 10 to the 6, 0 meters per second. Thank you for watching.